is Miss List, and today we are taking a look at AP Chemistry 4.7, which is on types of reactions. Now, this first little bit I have actually already introduced in 4.1 with the 5 basic types of reactions. If you remember our synthesis reaction, I lovingly call the marriage. This is 2 elements combined to form one single compound on the right, and we've got a real life example. Over here, we've got sodium going with chlorine to form NaCl. A decomposition would be if synthesis is the marriage, then a decomposition is the divorce. So it's kind of the opposite of what we see here in the marriage. We have one compound breaking apart into 2 single elements, and then we've got an example of potassium chlorate breaking apart into KCl and oxygen gas. Our single replacement, I like to call the homewrecker, which is very silly, but it helps you remember. We have B and C, which is a couple, and A is the homewrecker. They're gonna wreak havoc and break up B and C, and then A links up with either B or C. And who A links up with depends on the charge. So for example, in our real life single replacement reaction, we've got magnesium reacting with hydrochloric acid. Magnesium is our homewrecker. It's going to link up with the chlorine, not the hydrogen, because of the charge. Magnesium's positive. It's going to take the negative ion, being chlorine, to form MgCl, and then hydrogen ends up by itself. A double replacement reaction, I call this a wife swap. So this is where both partners trade places. So in our example, we have A paired with B and C paired with D. And on the right-hand side, we've got A and D linking up, and then C and B link up. So this includes acid and base reactions. They usually fall under a precipitate or under double replacement, as do precipitation reactions. In our real life example, we've got lithium chloride that's going to break apart, and lithium is going to hook up with nitrate. Again, that has to do with charge. Lithium is positive, nitrate's negative. We always want to make sure that we're putting an ionic compound together that has a positive going with a negative. And then finally, combustion. I don't have a special name for combustion that helps you remember it, but is the most specific type of reaction. It is a hydrocarbon, so it has to be some C and H compound. That's why it says X and Y, because we can have any number of C's and any number of H's. And it's very specific. It has to be reacting with oxygen, and the products will always, always, always be carbon dioxide and water. Now, one thing to note that it can, our hydrocarbon, the CXHY, can contain oxygen. But the main thing that we want to see is those carbons and hydrogens specifically reacting with oxygen to form CO2 and water. This real life example over here, C3H8, is also known as propane. So this is propane gas reacting with oxygen to form CO2 and water. We covered most of that in the introduction to this unit. Now we're going to introduce a little bit more detail on a new type of reaction that you may or may not be familiar with, and that's called an oxidation reduction reaction, which we often abbreviate as redox. Any of the above types can be redox except double replacement. Double replacement will never be an oxidation reduction reaction. So, an oxidation is the loss of electrons by an atom, ion, or atoms in molecules during a chemical reaction. And reduction is the gain of electrons. You cannot have one without the other. If oxidation is happening, then reduction is also happening. There are lots of little ways to remember which one is which, but I always do Leo, the lion, says grr. And that means Leo, lose electrons for oxidation. Leo, the lion, says grr, gain electrons for reduction. There, like I said, are other mnemonics that people use. One is called oil rig. There are some other fun phrases, but this is the one that I learned when I was in high school, and I just never let it go. So Leo the lion says grr. So over here in this example, we have zinc, which in its normal state would have what we call an oxidation number of 0. And then on the right, we have zinc as a +2 ion. So in order to go from an oxidation number of 0 to +2, that means that a loss of electrons had to happen. So zinc, we would say zinc is being oxidized. Copper, on the other hand, is going from a +2 ion to its normal state, which would have an oxidation number of 0. So we have a +2 going down to a 0. It's being reduced in charge, if you will. And the way that we reduce a charge is to gain electrons. So a big part of oxidation reduction reactions is identifying who is being oxidized and who is being reduced. The way that we do that is by a set of rules for what we call oxidation numbers. So to determine which chemical in a species is being oxidized and which is being reduced, you assign oxidation numbers in a chemical reaction to represent each element that's present. So this is the list of oxidation number rules. Elements will always have an oxidation number of 0. And this includes when they're in their natural state. That's why zinc with no ionic charge would be 0. And this also includes our diatomics. So for example, oxygen gas is O2, and that is its normal state that oxygen exists, so it would also have an oxidation number of 0. Hydrogen, when it's in a compound, will almost always be +1, except when it's a hydride ion. It would be -1. Oxygen is always going to be a -2 unless it's peroxide, and then it becomes a -1. And then oxidation numbers for monoatomic ions will usually equal their charge. So group 1, we know, always form +1 ions. Group 2 will always form +2, and fluorine is always going to be -1. The sum of oxidation numbers must add to 0, and the oxidation numbers of polyatomic ions will always add to the overall charge of the ion. The other thing that's introduced here is a special subcategory of reactions called acid-base reactions, and typically when we do acid-base reactions, it's important to understand what is acting as the acid and what is acting as the base. So in AP chemistry, we focus on the Bronsted-Lowry definition of acid and base. There are actually 3 different definitions for acids and base, but for AP Chem, we focus on the Bronsted-Lowry, which has to do with an acid is the proton donor and the base is the proton acceptor. When we talk about an acid-base conjugate pair, we're pairing something that is an acid with its specific conjugate base. So here in this example, we have water, and if I look from the left side to the right hand side, it looks like water is giving a hydrogen over to NH3. That's why it becomes NH4, and then the water becomes OH. So because water is who is donating the hydrogen, water is acting as my acid. NH3 is acting as the base because it is receiving the hydrogen. On the right-hand side of the equation are what we call the conjugates of the acid and base. So this becomes important again in Unit 8 when we deep dive acids and bases and talk about something called buffers. But essentially, the acid, what is acting as the acid on the left-hand side, becomes the conjugate base. And those are linked together as an acid-base conjugate pair. So sometimes on multiple choice questions, they love to identify the conjugate acid-base pair, and we want to make sure that we are identifying that correctly. So the acid on the left-hand side is going to be the conjugate base on the right. And then similarly, the base becomes what we call the conjugate acid. Now, it is important to know that acids and bases can be described as strong or weak. We'll discuss those in 4.9, I believe. Strong and weak don't necessarily, it's kind of a misnomer because weak does not mean ineffective. When we use the term strong and weak, we describe the extent at which a substance will disassociate in a solution. Strong means that it will completely separate, but a weak acid only partially separates. And note, this is different than concentration and dilute that refer to the molarity. So with concentrated and dilute, we're talking about the molarity of the solution, because you can be a strong acid. For example, strong acid, one of them is HCl, but you can have a very small molarity and make it not concentrated. So that is the problem that some students have, is keeping those two thoughts separate. All right, let's look at a few examples. Here we are identifying what the oxidation number for each of these would be. And so for letter A, they're asking us about what would carbon's oxidation number be. Carbon's oxidation number is dictated by oxygen. Oxygen is always going to be a -2, and I have 2 of them. So in order for this to be neutral, carbon in this case would have to be a +4. S and S -2, well, they told me the answer. It's -2. So whenever something has an ionic charge, we take that as the charge. This is sulfur with no charge, and remember, anything in its normal existing state is going to have an oxidation number of 0. Over here, we've got a couple of ions, and remember, the key with the ions is that the overall charge doesn't need to equal 0, it actually needs to equal -2. So I'm going to come over here, and oxygen is always -2, and there's one exception for when we have peroxide, but we don't need to worry about that because that is not peroxide. So if I have 4 oxygens at -2, that gives me -8. So I need to figure out what would sulfur need to be in order to give me the overall charge of -2. If it was +8, then this would add to 0. And that's not the goal, because this is a polyatomic ion. I have to match what the polyatomic ion's charge is. So if sulfur was a +6 with the -8, that would still leave me a net charge of -2. And that's why sulfur in this compound is a +6. If we compare that to the one below it, which is sulfite, we only have 3 oxygens. So that gives me a negative charge of -6. Again, I have to equal out and get my net charge to be -2. So in this case, the sulfur would be acting as a +4, because +4 and -6 still maintains that -2 charge. So outside of the few rules that we listed, elements can have different oxidation numbers. Group 1 tends to stay the same, group 2 usually the same, and then oxygen and hydrogen, and then fluorine. Everyone else, it's kind of an all skate. That's why I did these particular examples. In B, we've got an example where sulfur is -2, C, sulfur is 0, D, sulfur is +6, and E, sulfur is +4. So we know that a lot of times when you learn the periodic table, you learn charges for each group, but it's a lot more complicated than that. So for manganese with oxygen, I have 4 oxygens, which when I add them up is going to give me a -8. And this time, a minus charge, the 1 is assumed, so that's -1. So if I need to have a net negative charge, then that means the manganese has to be a +7 in order to get that to work out. In number 2, it says for the following, balance the equation, then write a net ionic equation, then determine what is being oxidized and what is being reduced. So here, I notice I have 2 chlorines, so I need to put a 2 in front of HCl, and that actually helps me because I needed 2 hydrogens on the right. Now, my net ionic equation, remember I can break apart anything that is aqueous. So I can break apart hydrogen and I can break apart chlorine. That 2 counts for both of them. And then on the right-hand side, I can break apart zinc and I can break apart chlorine. Now, the only one that would cancel would be my chlorine. So I'm going to rewrite this. I have zinc solid plus 2 hydrogen ions in aqueous solution. And that's going to form zinc 2 plus, and that's an aqueous, plus hydrogen gas. All right, final step is they want us to determine the oxidation states and then determine who is being oxidized and who is being reduced. So I'm going to switch to a new color. That will just help us. Zinc is going to be in its elemental state, so it actually has an oxidation number of 0. Here, hydrogen has a charge, +1, so that is the oxidation state. Similarly, here with zinc, zinc is going to be +2, and then hydrogen in its natural state is 0. So, to determine who is oxidized and who is reduced, we look from the left-hand side over to the right-hand side, and we see that zinc has gotten more positive. That means it has lost electrons. And then hydrogen went down in charge. It went from +1 to 0, which means it has gained electrons. So I would say that zinc is being oxidized. Remember, Leo, lose electrons, oxidation. So zinc is what's being oxidized. And hydrogen gained electrons, which means it is being reduced. All right, let's look at a few more examples of this. First thing I need to do is to balance my chemical equation. I notice that I have 2 nitrates, so I'm going to put a 2 here. That counts for sodium as well, which actually ends up helping me because I needed 2 sodiums. Now I'm going to break apart anything that is aqueous and then rewrite my net ionic equation. So cobalt +2, and then I have 2 nitrates, and then I have 2 sodiums, and then HPO4 is a polyatomic ion, and it's going to have a -2 charge. And then I cannot break apart my solid, so that has to stay as COHPO4 solid. And then I can break apart my sodium nitrate, so I have 2 NAs plus 2 nitrates. I'm going to cancel what appears on both sides, and that's going to be my nitrate and my sodium. And I'm going to rewrite what's left over. So I have cobalt +2, and that was an aqueous solution, plus HPO4 -2, and that was in solution. And it's going to form COHPO4 solid. Let's check this out. If we look at the oxidation numbers for this particular example, cobalt is +2. They tell us right there in there. If I look at hydrogen, almost always is +1. And then PO4, oxygen is going to be -2, and I have 4 of them, so that's -8. And then remember, I have to make sure that I match this net charge of -2. And so when I look at that, that tells me that probably this is a 5, because together these guys make a +6, and when combined with -8, I still maintain that -2. What we find on the right-hand side is that these charges end up being the same. This is going to be +2, +1, +5, and then -2. So we actually see no change in oxidation numbers. So this one is actually not redox. Tricky, tricky. A couple more, and then we'll look at some acid-base examples. On the next one, hydrogen is +1, and we have 4 of them. That means that carbon in this case is going to be -4. Oxygen is in its ground state, which is going to be 0. Here, hydrogen is going to be +1, and we have 2 of them. Oxygen is -2. And then we actually did CO2 earlier. It's -2 for each of the oxygens, and then +4 to cancel that out. Now, I can't write a net ionic equation for this because we actually are already, there's nothing that I can break apart. Remember, with net ionic equations, I can only break apart my aqueous. And here I have gas phase, liquid phase for water, and then more gas phase. So I can't break anything apart. I do need to balance this though. I have 4 hydrogens, so I need to put a 2 here. And then that gives me actually 4 oxygens on the right, so I'd put a 2 here. As far as oxidation and reduction, I noticed that oxygen went from 0 to -2, which means it has gained electrons. And then carbon went from -4 to +4, so it actually has lost electrons. So remember our saying, Leo, if you lose electrons, that's oxidation, and if you gain electrons, that's reduction. So carbon lost electrons, that means it was oxidized. And then oxygen is the one that gained electrons, so that one is the one that's going to be reduced. All right, final oxidation reduction reaction. We do need to balance this because, let's see, I have 2 hydroxides and 2 hydrogens. Sometimes it helps if you write water as HOH, because that helps me visualize a little bit more that I have 2 hydroxides and 2 hydrogens, so this just needs a 2 here. As far as doing my net ionic equation, on the product side, we have a solid and a liquid, so there's actually nothing that I can cancel on the right-hand side. Plus, I can actually realize that this is a double replacement reaction. H goes with OH, Ca goes with SO4. And what do we know about double replacement reactions? They are not redox. So I actually can stop this one. I don't need to go all the way through it like I did previously because I recognized that it was double replacement. Up here, we could have done that, but I wanted to go through the process of you seeing how the oxidation numbers did not change. But if you go back and look, it is double replacement because cobalt is hooking up with HPO4 and sodium is hooking up with nitrate. So again, double replacement, not redox. I went through those numbers though so you could see it. Now that I know that and I've proved it, I don't think we need to go through the oxidation numbers on letter D. Final example here, we go back to our acid and bases, and what we want to look for is where is the hydrogen going and who is donating and who is receiving. So it looks like HCl is sending a hydrogen over to water. So that means HCl is acting as the acid, and since water's receiving it, it's acting as the base. And then remember, whatever was the acid becomes the conjugate base on the right-hand side. So Cl is going to be my conjugate base. And then whatever was my base, water, becomes the conjugate acid on the right-hand side. All right, next one we have, straight mark. We've got ammonium with water. And this time, water is sending a hydrogen over to ammonium. That's why I have the ammonium ion on the right. And then hydroxide is after that hydrogen has been transferred. So in this case, water is acting like the acid. Water can actually act like an acid or a base depending on who it's with. It's one of the fun things about water. And NH3 is acting as my base because it is receiving the hydrogen. The acid becomes the conjugate base. So water was my acid. It's going to become the conjugate base on the right-hand side. And then my base becomes the conjugate acid. So NH3 was the base. On the right-hand side, it is a conjugate acid. All right, that is 4.7. The next 2 sections, deep dive, redox, and acid base a little bit more. I will see you next time.